In this video, I want to familiarize you with the idea of a limit, which is a super important idea. It's really the idea that all of calculus is based upon. But despite being so super important, it's actually a really simple idea. So let me draw a function here. Actually, let me define a function here, a kind of a simple function. So let's define f of x. Let's say that f of x is going to be x minus 1 over x minus 1. And you might say, hey, Sal, look, I have the same thing in the numerator and the denominator. If I have something divided by itself, that would just be equal to 1. Can't I just simplify this to f of x equals 1? And I would say, well, you're almost true. The difference between f of x equals 1 and this thing right over here is that this thing can never this thing is undefined when x is equal to 1. Because if you set, let me define it right, let me write it over here. If you have f of, sorry, not f of 0. If you have f of 1, what happens? In the numerator, you get 1 minus 1, which is, let me just write it down. In the numerator, you get 0. And in the denominator, you get 1 minus 1, which is also 0. And so anything divided by 0, including 0 divided by 0, this is undefined. This is undefined. So you can make the simplification. You can say that this is the same thing as f of x is equal to 1, but you would have to add the constraint that x cannot be equal to 1. Now this and this are equivalent. Both of these are going to be equal to 1 for all other x's other than 1, but at x equals 1, it becomes undefined. This is undefined, and this one's undefined. So how would I graph this function? So let me graph it. So that is my y is equal to f of x axis. Y is equal to f of x axis. And then this over here is my x axis. X axis. And then let's say that this is the point x is equal to 1. This over here would be x is equal to negative 1. This is y is equal to 1 right up there. Yeah, I could do negative 1, but that won't matter much relative to this function right over here. And let me graph it. So it's essentially for any x other than 1, f of x is going to be equal to 1. So it's going to look like this. It's going to look like this. Except at 1. At 1, f of x is undefined. So I'm going to put a little bit of a gap right over here. This circle to signify that this function is not defined. We don't know what this function equals at 1. We never defined it. This definition of the function doesn't tell us what to do with 1. It's literally undefined when x is equal to 1. So this is the function right over here. And so once again, if someone were to ask you what is f of 1, you'd go, and let's say that even if this was the function definition, you would go, okay, x is equal to 1. Oh, wait, there's a gap in my function over here. It is undefined. So let me write it again. It's kind of redundant, but I'll rewrite it. F of 1 is undefined. But what if I were to ask you, what is the function approaching as x equals 1? And now this is starting to touch on the idea of a limit. So as x gets closer and closer to 1, so as we get closer and closer x's to 1, what is the function approaching? Well, this entire time, the function, what's it getting closer and closer to? On the left-hand side, no matter how close you get to 1, as long as you're not at 1, you're actually at f of x is equal to 1. Over here, from the right-hand side, you get the same thing. So you could say, and we'll get more and more familiar with this idea as we do more examples, that the limit as x, and lim, short for limit, as x approaches 1, of f of x, is equal to, as we get closer, we can get infinitely close to 1, as long as we're not at 1. And our function is going to be equal to 1. It's getting closer and closer and closer to 1. It's actually at 1 the entire time. So in this case, we could say the limit as x approaches 1 of f of x is 1. So once again, has very fancy notation, but it's just saying, look, what is a function approaching as x gets closer and closer to 1? Let me do another example where we're dealing with a curve, just so that you have the general idea. So let's say that I have the function f of x, and let me just for the sake of variety, let me call it g of x. Let's say that we have g of x is equal to, I could define it this way. We could define it as x squared when x does not equal, I don't know, when x does not equal 2. And let's say that when x equals 2, it is equal to 1. So once again, a kind of an interesting function that, as you'll see, is not fully continuous. It has a discontinuity. But let me graph it. So this is my y equals f of x axis. This is my x axis right over here. Let me draw x equals 2. Let's say this is x equals 1. This is x equals 2. This is negative 1. This is negative 2. And then let me draw. So everywhere except x equals 2, it's equal to x squared. So let me draw it like this. So it's going to be a parabola. It'll look something like this. It's going to look something. Let me draw a better version of the parabola. So it'll look something like this. It looks something like this. Not the most beautifully drawn parabola in the history of drawing parabolas, but I think it'll give you the idea. I think you know what a parabola looks like. Hopefully, it should be symmetric. Let me redraw it because that's kind of ugly. Okay, so that's looking better. Okay, all right, there you go. All right, now this would be the graph of just x squared. But it's not x squared when x is equal to 2. So once again, when x is equal to 2, we should have a little bit of a discontinuity here. So I'll draw a gap right over there. Because when x equals 2, the function is equal to 1. When x is equal to 2, so let's say that, and I'm not doing them on the same scale, but let's say that, so this, on the graph of f of x is equal to x squared, this would be 4, this would be 2, this would be 1, this would be 3. So when x is equal to 2, our function is equal to 1. So when x is equal to 2, our function is equal to 1. So this is a bit of a bizarre function, but we can define it this way. You can define a function however you like to define it. And so notice, it's just like the graph of f of x is equal to x squared, except when you get to 2, it has this gap, because you don't use the f of x is equal to x squared when x is equal to 2. You use f of x, or I should say g of x. You use g of x is equal to 1. Have I been saying f of x? I apologize for that. You use g of x is equal to 1. So then at 2, just exactly at 2, it drops down to 1, and then it keeps going along the function g of x is equal to, or I should say, along the function x squared. So my question to you, so there's a couple of things. If I were to just evaluate the function g of 2, well, you look at this definition. Okay, when x equals 2, I use this situation right over here, and it tells me it's going to be equal to 1. But let me ask a more interesting question, or perhaps a more interesting question. What is the limit as x approaches 2 of g of x? Once again, fancy notation, but it's asking something pretty simple. It's saying as x gets closer and closer to 2, as you get closer and closer, and this isn't a rigorous definition, we'll do that in future videos. As x gets closer and closer to 2, what is g of x approaching? So if you get to 1.9, and then 1.999, and then 1.999999, and then 1.9999999, what is g of x approaching? And or if you were to go from the positive direction, if you were to say 2.1, what's g of 2.1? What's g of 2.01? What's g of 2.001? What is that approaching as we get closer and closer to it? And you can see it visually just by drawing the graph. As g gets closer and closer to 2, and if we were to follow it along the graph, we see that we are approaching 4. Even though that's not where the function is, the function drops down to 1, the limit of g of x as x approaches 2 is equal to 4. And you can even do this numerically using a calculator. And let me do that, because I think that will be interesting. So let me get a calculator out. Let me get my trusty TI-85 out. So here is my calculator. And you can numerically say, okay, what's it going to approach as you approach x equals 2? So let's try 1.9. For x is equal to 1.9, you would use this top clause right over here. So you'd have 1.9 squared. And so you'd get 3.61. Well, what if you get even closer to 2? So 1.99. And once again, let me square that. Well, now I'm at 3.96. Well, what if I do 1.999? 999. And I square that. And I square that. Now I'm getting a 3.996. Notice I'm getting closer and closer and closer to our point. And if I got really close, 1.999999999 squared, what am I going to get to? It's not actually going to be exactly 4. This calculator just rounded things up. It's going to get to a number really, 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 really close to 4. And we can do something from the positive direction too. And it actually has to be the same number when we approach from the below what we're trying to approach and above what we're trying to approach. So if we try 2.1 squared, we get 4.4. If we do let me go a couple of steps ahead. 2.01. So this is much closer to 2 now, squared. Now we're getting much closer to 4. So the closer we get to 2, the closer it seems like we're getting to 4. So once again, that's a numeric way of saying that the limit as x approaches 2 from either direction of g of x, even though right at 2 the function is equal to 1 because it's discontinuous, the limit as we're approaching 2, we're getting closer and closer and closer to 4.